Well, hi there. We are so close to the end of the year. This is the last Monday of April, and we've got just this week. We're going to finish up lesson 6.4 today and tomorrow, and then we're going to spend Wednesday, Thursday, Friday doing review. And we're going to take our chapter 6 test next Monday, okay, week from today. And so, we're just really wrapping it up, and we'll do a few lessons after that, and then we're heading to the final exam. So remember, juniors, you have to take the final exam, so plan on that. Seniors, you can be exempt from this final exam if your grade is an 83% or higher. All right, so that'll be our goal. Today we're going to work on finishing up differential equations, and we've worked on so many different ways to solve differential equations. This is the last strategy today that we'll be using for separable differential equations. But before we jump into that, we need to do some quick algebra rules here. So we want to make sure that we're good and solid on our algebra. So the idea here is that we get y alone, that we do something to both sides to get the y alone. So we want to, in the first equation, we want to get rid of this ln somehow. So the only way you can do that is by using an e, and you have to use an e on both sides. Now you can't use multiple e's like that. Okay, that would be illegal to do more than one e, but what you would end up doing is once the e and the ln cancel out, you'll have y equals e to the parentheses 3x minus 2. So it's those parentheses I want to emphasize, that we remember to apply that when we get y alone. For the next example, we want to get the absolute value alone. And that's something a lot of people forget how to do that when you remove the absolute value. When you remove it from one side, you have to put something on the other side. Okay, that's the rule of math. It's the balance. So when you get y by itself, what do you put on the other side? Well, you put a plus or minus in front of the parentheses. So that parentheses is still important, and this time it's a plus or minus that's removed. Okay, and then y squared. How do we get y by itself there? Now, most people remember that they use a square root, but a lot of times they'll forget that a square root has the plus or minus in front as well. So 3 things we wanted to review about how to get y by itself. Another thing we want to review is something about adding and subtracting powers. Now the addition and subtraction of powers, so you'll see we've got add, subtract, subtract, add, okay? The addition and subtraction of powers translates into a product or a quotient, and so that's a property that we want to review because we'll need that today as well. And so the first one, having this addition here, so that would turn into for us a product. So that would be equal to 3 to the x times a separate 3 to the 2y. So those two things get separated into a product. Now similarly, a subtraction would turn into a quotient expression. And so that means that we'd have 3 to the x divided by a separate 3 to the 2y. So remembering that those are properties. Okay, we've got another subtraction here. So that'll give us e to the y over e to the x squared. Okay, subtraction always is changing into a quotient. And then finally we have addition again. And so the addition would turn us into an e to the x times an e to the ln y. Now I did this one as a special example because e to the ln also cancel each other out here. And that leaves us with e to the x times a plain y. And more often than not, you'll see the y in the front and an e to the x in the back. So that'd be the most common way to write that. All right, so those couple algebra reviews before we move on to the new things. The other thing we want to review is what we've done in chapter 6 so far. So chapter 6 we dealt with, this was lesson 6.1. We dealt with the question, do you recognize a simple antiderivative? Okay, a simple antiderivative meaning that 1 over x turns into the ln of the absolute value of x, or that cosine as an antiderivative turns into sine, or that x turns into x squared over 2. Okay, those are simple antiderivatives. So we reviewed all of those in 6.1. In 6.2, Then we moved into some of the other questions. Well, what if it has parentheses? Or what if it has the word of, like the square root of? Or, is it a product? Is it a quotient? Does it have a higher power? All these questions. That moved us into using a U substitution. And if we answered yes to any of those questions, there we go. If it did have parentheses, or it did have the word of, or was a product or a quotient, we tried the U substitution. And hopefully we got something that simplified well. Okay, so then if it didn't simplify well, okay, if it doesn't work out, if it's not simplifying well, then we want to try a different U. Maybe you picked your U wrong in the first place. All right, and so if it does not simplify the way you want it to, then try a different U and see if that helps. But if that still doesn't help, if it still does not simplify well, then that took us into 6.3. And if it did not simplify well, then we tried the Lipit test. Okay, the Lipit rule. So, do we have one of the 5 Lipit parts? Do we have an L or an I, or do we have a P or an E or a T? Do we have one of those? So if you have an L and an I, then you're going to do integration by parts, which is what we were working on last week. That was where you had just the beginning, and then we would cross multiply here, and then this last one would also be paired with that using an integral. That was if we have an L or an I. Let me draw my arrow. Okay, so an L or an I leaves to that. But if we only have a P, an E, or a T, well then we can do tabular integration. And if we have tabular integration, that gets set up like this with a long table. And then we've got all kinds of diagonal pairings with a subtraction, and then diagonal, and then another diagonal, however we work that out. But that only applies to PET, okay? Doesn't apply to the other kind. So that was all the stuff that we covered in 6.3. But there's still some questions that come up after that, all right? So when you're working with these parts and you're using the Lipit rule, there's still problems that can't be solved. It doesn't work out nicely. The the diagonal lines don't pair up well. So some of the questions we have, well, what if we have 2 of the same kinds of a part? Is there such a thing as LLIPT, like if you have 2 L's? Or is there such a thing as LIPEET? Okay, could I do that? And no, you can't use this method. You can't use integration by parts. You can't use tabular if you have 2 of the same kind. And then another question is, what if you have different variables? What if you have a log that has an x, but then you have a trig that has a y? Different variables. So you have different parts. You have one log and one trig, but they have different variables. And what do you do? So that's this last strategy that we're going to talk about today. Okay, if you've got different things. All right, so let's tackle that. So let's say part of your function has an x variable. And let's say the other part of your function has a y variable. These are considered different parts. And there are still 4 parts altogether. So one of them is the x part, one of them is the y part. Well, then what are the other parts? The other parts are the differentials, and you'd have a dx and you'd have a dy. So there are 4 distinct parts to a differential equation. The differential equation is arranged with the dy on top and the dx on the bottom. So that takes care of 2 of the parts. And then the other 2 parts, the f part and the g part, can be arranged either using multiplication or using division. So if we have multiplication, we might have f of x times g of y. That might be a multiplication in the way it's arranged. Or we might have the x part on top and the y part on the bottom. That could be how it would be arranged. Or we might have the y part on top and the x part on the bottom. That's also a possibility, but it has to be multiplication or division, okay? These arrangements are called separable differential equations, okay? 4 parts, so part 1, 2, 3, and 4, arranged in these 3 different scenarios. And remember, only products or quotients can be separated. If it's not, if it has addition, if it has subtraction, if it's not written in the form of a product or quotient, then it's something that is called non-separable, and it's not possible for us to do with this method. In fact, it won't be possible for you to do with any method other than a Math 9 on your calculator until you take an upper level calculus class and learn something else. But we are only going to deal with products and quotients. So if you have identified a problem with 4 parts, 2 different kinds of variables, and it's all a product or a quotient, then you can do the process of what's called separation. And the process starts with cross multiplying. So you cross multiply first. Then you move the parts of the problem around so that the like variables, all the x's or all the y's, that they're on the same side of the problem. And remember, you can only multiply or divide. Those are the only 2 strategies that you can use in this method. So we're going to practice the process of what's called separation. So here's an example of a differential equation that's in 4 parts. So let's count up our parts. We've got the dy part, the dx part. Here is the part that is the part of x, okay, the function of x, and then here's the part that is the function of y. So we do have our 4 different parts, and this is a multiplication problem, multiplication on one side, division on the other, so we can use the separation method. So the separation method says to cross multiply. So you drop a 1, and then you do your cross multiplication. All right, what do we have? We have dy equals negative 3x y squared times dx. So now we want to rearrange so that all the parts that are y are on one side and all the parts that are x are on the other. So this is my part that's y, and so I want to move it, and the only way I can move it is by division. So I'm going to divide, and so I'll have dy over y squared equals negative 3x times dx. So now I have all the parts of y on one side and all the parts of x on the other. An even better way to write it would be to write this with a negative power. So y to the negative 2 times dy and negative 3x times dx. So if you can even write it as all multiplication, that's even better. So we cross multiplied, and then we moved the parts to gather the similar terms on the same side. Let's practice that again. Okay, here is another differential equation. Let's see if it has 4 parts. I've got 1 part, 2 parts. I have a y part and an x part, except I have subtraction. And I can't use subtraction in a separable differential equation. I have to rewrite it as either multiplication or division. Well, that's why we reviewed the powers. We know that e to the 2y could be written in the numerator, and e to the x would be written in the denominator. And so we're going to rewrite this as a quotient. So now I have division, and I will cross multiply my division. So now I'll have e to the x times dy, and I'll have e to the 2y times dx. So now I've got the cross multiplication done. Now I've got to move some things. Okay, I'm going to want to move this because it's on the wrong side. It's an x part, but it's on the left side. And I want to move this because it's a y part, but it's on the wrong side. So I'm going to move them with division. So what I end up with is dy over e to the 2y, and then I end up with dx over e to the 2x. But it's always better to write that in multiplication instead. So that would be e to the negative 2y. So instead of being in the denominator, now it's in the numerator. And e to the, excuse me, I shouldn't have a 2 there, should I? Let's get rid of that. Okay. So e to the negative x and then dx. So always best, if you can, to write it instead of a division problem, to write it as a multiplication problem. Okay, now we have a differential equation. So we've got our parts here. We've got one part, two parts. Here's our y part. Here's our x part, except I have addition again. Except in this case, the plus x is not part of the power. It's just a plus x. And there is no way for me to take this kind of addition and write it as a multiplication problem. So this is what we would call non-separable. And we'd say I can't do this problem in any other way that I know so far. So as long as you identify it as non-separable, then you would move on. All right, so let's review what we have. The process of separation. We cross multiply. We move the parts so that the like variables are on the same side. And once we've done that, we're going to add the step of apply an integral to each side separately. Okay, so that leads you to a summary of the steps. The first step is separate. Once you do that, the next step is integrate. So we've practiced the separate part of the process. Now we're going to integrate. Separate, integrate, separate, integrate. So you'll hear me just kind of use that. Oh, did you try separate and integrate? And, that would be like, oh, did you try U-sub? Oh, did you try lipit? Those are questions I just ask to help you kind of, jumpstart the process of what you need to do. So let's try separate and integrate here. We've already practiced the separation of this. Okay, we drop a 1, we do our cross multiplication. We end up with dy equals negative 3xy squared dx. We complete the separation by moving the y squared term to the other side and writing it as a product. So it'll be y to the negative 2 dy and negative 3x dx. Okay, that completes separation. Now we want integrate. So I'm going to put an integral sign on both sides. And I'm going to work on the integration. So the integration becomes y to the negative 1 divided by negative 1 plus the constant c. And on the other side, we get negative 3x to the second divided by 2, also plus c. Now you can't have two different plus c's. So we're going to call this one a c1 and that one a c2. So we've done the separate and we've done the integrate. Okay, so that's the portion that you're at right now. You have an antiderivative on both sides. We could write this a little bit better. We could say, oh, this is negative 1 over y plus the constant, and negative 3/2 x squared plus the second constant. Okay, let's try another one. Is this a separate and integrate situation? All right, well, I've got one part for dx, one part for a dy. I have a 2x term in terms of x. I've got the y term here, that's my fourth. Oh, and then there's a fifth one. Will it still work? Well, let's try. Let's drop a 1 and then try the cross multiplication. All right, that gives me dy equals 2x times 1 plus y squared e to the x squared and then dx on the end. And so this is the part here I want to move. And I can only move it with addition, with multiplication or division. So I'm going to divide. So I'll have dy over 1 plus y squared, and then I'll have 2x times e to the x squared dx. So at least I have all the y's on one side and all the x's and on the other. That's the separate part. Now I'm going to try integrate. So I'm going to put an integrate on both sides. Now, can I integrate them? So let's look at this. Is it possible to integrate this? Well, this is one of the simple integrals that I hope you haven't forgotten about. This is an inverse trig integral. 1 plus y squared is the inverse of tangent. So this turns into tangent inverse of y plus constant number 1. Now on the other side, does this have a simple integral? And the answer is no. It doesn't have a simple integral because it has a product. Well, shoot, what do I do now? Well, we reviewed. Okay, we reviewed if it's not a simple integral, then my next step is to say, is it a product? Does it have an of? Does it have parentheses? What do we got here? And this is an of situation. This is 2x times e to the power of x squared. The word of there is your clue, and it's the power of x squared. So this is going to be a u substitution situation. So we can't just forget what we learned before. It's everything all put in together. It's the inverse tangent derivative, and now it's using the u substitution as well. So du over dx equals 2x, and we cross multiply that, and we find out that dx is equal to du over 2x, and we do our substitution. So my integral becomes 2x times e to the u, and then du over 2x. And those two x's reduce. So I'm left with the tan inverse of u plus constant c1. And on the other side, I have a simple antiderivative now of e to the u plus constant c2. And I can change my u back, and my u would get changed back to x squared. All right, so what about these plus c's now? I don't know if it's bothering anybody that we've got a c on both sides. We have a c1 and a c2. So if we are given an initial condition, we can actually figure out these values of what plus c turns out to be. So here are the steps you're going to follow if you're given an initial condition. Remember, the initial condition would be like an xy pair, and then you could plug that in. So here are the steps. Separate. That's always first. Integrate. That's always second. Then we're going to solve for c. And we're going to do that using the initial condition. So these two steps go together. Solve for c using the initial condition. And after you've done that and you've solved for c, our last step is going to be solve for y. And solving for y means get y alone. And we get y alone so that the solution looks like y equals blank, blank, blank. Right? We always want y alone at the end. All right, so let's put it all together and find these. So this is SI, SIS. Okay, now the middle part, this SI part, you're only going to do that if you have an initial condition. If you don't have an initial condition, then you'll do the first two, and then you'll jump down to here. Okay, but if you have an initial condition, then you'll go into the middle SI. So it's either SI jump down to S at the bottom, or SI, SIS if you have an initial condition. So let's try here with an initial condition. All right, we see that there are 4 parts, 1, 2, 3, 4 to this differential equation. We will cross multiply and work on separating. So we cross multiply and we get 2y dy. On the other side we get x dx. So that's the cross multiplication, and everything is nicely separated already. All the y's are where they should be, all the x's are where they should be. So now we're going to integrate. We're going to integrate both sides. Okay, and the simple integral is going to be y squared plus c1. And the other simple integral will be 1/2 x squared plus c2. All right, now we're going to deal with the c1 and the c2. We're going to move the c's together on the same side. So I'm going to subtract a c1 from both sides. Okay, by subtracting the c1, I get y squared by itself. I get 1/2 x squared. And then a constant minus another constant is still a constant value. And so one constant subtracted another is just a single c without the subscripts. So c2 minus c1 is just going to be plain c. Once I do that, I'm going to plug in my initial condition over here, and I'm going to put 2 in for x and 3 in for y. So let's do that. So -3 goes in for y, and 1/2 2 goes in for x, plus c. So that's 9 equals 1/2 of 4 plus c, or 9 equals 2 plus c, and c turns out to be the number 7. So we have done S for separate, I for integrate, S for solve for c, and then I for the initial condition. And now we're ready for our last S, which is solve for y. So we are going to start this question over kind of from this spot right here. And we're going to say y squared equals 1/2 of x squared. Now plus 7 is what I figured out. And we want to get y by itself. And so we're going to take the square root combined with a plus minus over the entire quantity, 1/2 x squared plus 7. So you need the plus and the minus, and you need the square root to cover the 7 as well as the 1/2 x squared. So that's the complete SIS process. So let's practice that a couple more times. Okay, here's our differential equation. We see the parts, but we see that we have a subtraction in the parts. So we want to write that as e to the 2y divided by e to the x. Okay, so we're going to eliminate that, and then we will do our cross multiplying. So we'll have e to the x times dy and e to the 2y times dx. So we've seen this already, where we want to get, now they're on the wrong side. So dy would be divided by e to the 2y, and dx would be divided by e to the x. But again, it's really preferable not to write it like that, but to use negative powers to write it differently. So I'm going to, instead of writing e to the 2y, I'm going to write e to the -2y. And I'm going to erase that e to the 2y down there. All right, and on the other side, instead of writing e to the x, I'm going to write e to the -x. So let me clean that up too. Okay. The reason we do that is so that when we integrate, it's a lot of an easier integral to do. All right, so separate, integrate. E to the -2y divided by -2, because that's the chain rule, plus the first constant. And then e to the -x divided by that chain rule, plus the second constant. And then I'm going to subtract c1 from both sides, which essentially erases it on the left and then combines it just to a plus c on the right. So there's where we're at. So S for separate, I for integrate, S for solve for c, using the initial condition, I. All right, so 0 is my initial condition. 0, 0, and I'm going to plug those in for x and y. So I'm going to get e to the -2 times 0 over -2 equals e to the -0 over -1 plus c. And remember that e to the 0 is just 1. So that's 1, and this is 1. So what do we have? We have -1/2 equals -1 plus c. So add 1 to both sides, and c turns out to be half. All right, so then I'm going to finish my problem. I'm going to kind of draw a dividing line, and I'm going to start from this equation, and I'm going to put my c in. So I'll have e to the -2y over -2 equals e to the -x over -1 plus the constant half. And now we want to solve for y. We want to get y alone. And the way we do that is by multiplication. Everything by -2 times by -2 times by -2. All right, so that gives me e to the -2y, because the -2 cancels out the -2. And then 2 e to the -x minus 1. Now I want to get rid of the e. And the only way I can get rid of the e is by using a natural log on both sides. So that would get rid of the e, but it would put a natural log around the quantity 2 e to the -x minus 1. And then I divide everything by -2. So the natural log of 2 e to the -x minus 1, the whole thing over -2. So now I have y alone, and I'm done. S for separate, I for integrate. S for solve for c using the I initial condition, and then S solve for y. All right, this is our last one. Try this together. SI, SI, S. Okay, let's drop the 1 and then do a cross multiply. All right, so what do we have? We have dy equals x squared y squared times dx. And so we have to move this term by division. So divide everything by y squared, but write it as a negative power. So I'm going to have y to the -2 dy, x to the +2 dx. So that's your separate. Now you want your integrate and find the simple integral. So we're going to have the simple integral is y to the -1 over -1. And the simple integral plus c1. And then x to the power of 3 divided by 3 plus c2. But then we're going to combine the c's. So I'll get rid of c1 and I'll get rid of that. And so now we have our c. Okay, separate, integrate. Now solve for c using the initial condition. So our initial condition is x is 0 and y is 3. So let's substitute that in. Before I do that, I think I want to rewrite this better. So I have a -1 and a y to the -1. So that's -1 over y in the denominator. That's just cleaner. It's just a better way to write it. Okay, now I'm going to put in my 0 for x and my 3. So this will give me -1 over 3 equals 0 cubed over 3 plus c. And of course, 0 cubed is 0, so c is -1/3. All right, let's finish it up. I'm going to draw my dividing line for my work. I'm going to start from this line here, and I'll have -1 over y equals x to the 3rd over 3 minus 1/3. Now I want to get y by itself. Okay, I want to get y by itself. Well, do you notice that we have a common denominator of 3? So we're going to write this as x cubed minus 1 over 3. Now we're going to cross multiply. When you have y in the denominator, you can't just flip everything. There's no legal flipping. You want to multiply by cross multiplication. So that gives me -3 equals x cubed minus 1 times y. And now we want to move the x cubed minus 1 so that we can have y by itself. So when we do, y will be by itself in negative 3 over, and then the quantity x cubed minus 1 ends up in the denominator. So we've successfully and legally gotten y by itself. All right, so you have done the hard work of separating and integrating and then using a constant to find your plus c. So I wish you good luck on this. We will finish chapter 6 tomorrow, and then we'll spend Wednesday, Thursday, Friday reviewing. Friday will be an optional Zoom at 8:30, and I'll just be available to answer questions coming up on the test. All right, I'll see you on Wednesday. Hope you guys have a good start to your week.